This presentation is about interval analysis using the so-called boxes abstract domain. It's based on work by the people listed here. I'm Harald Sondergaard, and I'll take you through the main ideas of what we call range decision diagrams and how we use them for disjunctive interval analysis. So there are situations that call for path-sensitive analysis. I've taken this example from a recent paper. Often, for example, when you translate state machines into programs, you get programs like this where some state variable or phase variable controls the flow. In this case, it's S. And if you spend a little time reasoning about this program, it is not hard to see that it will take first one branch, then another branch, then will be caught in a third branch in an infinite loop. And if you ask about the final value of, say, B, it is possible to convince ourselves that it ends up having value 3. However, unless you do the analysis in a path-sensitive way, you won't really be able to tell. But abstract domains that are closed under disjunction give us a simple and disciplined approach to a path-sensitive analysis. However, they tend to also be costly and are rarely used. But there is one abstract domain which was introduced at this conference 11 years ago that does provide an example of a useful abstract domain for interval analysis that is closed under disjunction and negation as well as conjunction. And that's the so-called boxes domain. So basically it allows us to express arbitrary Boolean combinations of bounds constraints. And there's an example down here that shows you how I can have a disjunction of conjunctions of bounds constraints, and above it you see the geometric interpretation of that. Now, Görfinkel and Schachte used, for their implementation of boxes, they used something called linear decision diagrams, or LDDs, and here is an example. That was a data structure, a DAG, that they had previously explored. They introduced it in work with Ofer Strickman. They were after a canonical representation for formulas in quantifier-free linear arithmetic. As you can probably guess, the idea here is to generalize RDDs, so that depending on the truth or falsehood of a node that represents a constraint, a bounds constraint, there are edges, two possible edges out of the node. There's a true edge, and here dashed, shown dashed, there's a false edge that you take if the constraint evaluates to false. And there are two sinks. I've drawn true down here, but there's also a false sink which we just leave out together with edges going to it. And that's just to avoid clutter in these diagrams. And now, apart from the usual ordering of variables that we are used to insisting on to get a canonical form, there's a need to also commit to a way of ordering the nodes that involve the same variable. So you can see here in any path from the root to a sink, we meet the variables in lexicographical order, assuming x comes before y. But also when there are several nodes involving x, we meet the stronger constraint first. And that gives us a canonical form. So LDDs are quite attractive, but they also have some drawbacks when used for practical analysis. So for one thing, they rely on a theory solver, and that sort of restricts the area, the kind of constraints that they support. The implementation of interval analysis in the Görfinkel and Schachte paper rely very heavily on a constraint substitution operation. As you traverse a diagram like this, the nodes may be, constraints may be replaced by other constraints. So it has a kind of syntactic flavor. And there is no support for the handling of nonlinear expressions. And so this has led us to explore a different data structure for the problem of disjunctive interval analysis. So we're proposing RDDs, or range decision diagrams. They tend to be more compact, and importantly, they, in a straightforward way, support the analysis also of nonlinear expressions. And this shows you an RDD for the same boxes element as on the left. It's a continuation of the diagram from the previous slide also, where there was this a disjunction of conjunctions or bounds constraints. And again, what we have here is a DAG with a root and two sinks, and again we leave out the false sink. And again, if you travel from the root to any sink, you will find the variables in lexicographical order. But now you can have any number of outgoing edges, and the idea is that each edge is labeled with an interval or a range, and if the particular variable is in that range, then that is the edge you take. Now in the paper we describe these RDDs formally. Here we'll just outline some of the abstract operations. All of the algorithms are in the paper, including an algorithm for widening, which is needed in this case because we can have infinite ascending chains of RDDs. The lattice operations are quite easy. Essentially, they generalize the classical recursive BDD algorithms that we know and love. The more tricky part comes when we deal with arithmetic expressions and assignments. And in general, best transformers do not exist in this particular case. So to see how an assignment is processed, suppose we have a boxes state as shown here on the left as an RDD. Suppose we want to, we need an assignment like this. Z is assigned the value of x times y. All the abstract operations that we have follow a certain pattern where we traverse the graph, we keep track of the relevant edges for relevant variables, and then update subgraphs as needed as we go, reconstructing the nodes, rebuilding the structure on the way back up. And so in this example here, we basically traverse this RDD. We keep track of the partial product xy so far, and then at the level for z, which is here, we create the relevant node. If there was a set node already, we would project it out first. And now we can create a node for z, and we can evaluate for each branch. We now know the range corresponding to the expression x times y, and of course that will be what we get here. So as I mentioned, LDD-based analysis does not lend itself to nonlinear expressions as we have here, which is why we picked this particular assignment. The best we can do is what is shown here on the right, where the overall bounds of x and y are used to calculate the bounds on x, just as we do in classical interval analysis. We've shown the result here in RDD form, but that's just because it makes it a little bit easier to compare with the other diagram, and you will notice the clear loss of precision in this case. Now you wonder, what if in this example z didn't come after the other two variables? In that case, we can pretend that z does follow the other two variables, as long as we then have a way of repairing any misordering on the way back up. And so variable hoisting is an important operation as part of some of these operations. So here's an example where x1 and x2 are in the wrong order. To swap them, well, there's enough information in that diagram up there that has left some subtrees A, B, C, D unspecified. There's enough information from this that we can now go and identify all the relevant split points. So for x1, we recognize here that we're going to need 4, 9, we're going to need 17. And so we can build this matrix of cofactors, of the relevant cofactors, for all the combinations of ranges of x1 and x2 that are relevant. So we do this, and now in order to build the correctly ordered RDD, well, it's essentially a matter of transposing this matrix. And again, all of the details of how we calculate this is in the paper. But here is what the RDD will look like after this transposition. And you'll recognize the various split points from before. Now, Graeme already had a boxes implementation based on LDDs, and so we have been able to compare what we call LDD boxes against the new RDD boxes. The test suite that we use is are the two categories, control flow and loops, from the software verification competition. And they are relevant and interesting for their own reasons. Altogether, there are 190 instances in this test suite. So what have we compared? Well, for RDD boxes, we use a static order where we have ordered the variable according to when they appear. And then for LDD boxes, we use two approaches. One is a dynamic ordering approach that was one of the contributions in the Gerfinkel and Schachte paper. And we also try to use the same static ordering as we have used with RDD boxes. And in terms of performance, this is the picture. On the whole, the LDD boxes end up being slower, and we have more timeout and memory out cases with them. If we look at the static LDD boxes, the picture is not all that different. It comes out more or less the same. And when we look at the precision and measure that in terms of how many of the assertions we can prove, well, out of 628 different assertions, dynamic LDD boxes are able to prove just under 500, and static LDD boxes just slightly more. With RDD boxes, we find that we can prove 510. So in summary, we have found that range decision diagrams are well suited for this problem of disjunctive interval analysis. The paper deals with the integer case, but the extension to rational or floating point number ranges should not be that difficult. And we have found that compared to LDDs for boxes, these range decision diagrams tend to be more compact. We can implement things without constraint substitution operation or any dependence on a theory solver. And we end up getting more precise analysis, mainly because of better analysis of nonlinear expression. So on the whole, the result is faster and more precise analysis.